Alrighty. So as Christine just said, my name is Heidi. My research title is Dr. DNN, and my mentor is Dr. Christian Shelton. I am from the Bourne College of Engineering, where my major is computer science. And I do have a very long exclusive title to Dr. DNN, but I feel like Dr. DNN felt more mysterious. But it is about finding contrastive examples through generative models. Now, before I begin talking about my research, I'd like to begin you off with a story. So when I was 5 years old, I started having problems with my right eye. I went to many doctors, many pediatricians, many different types of doctors, and all of them could not find what was wrong with me. I was diagnosed with 3 different types of cancers, all of which were debunked. And it turned out after seeing one neurologist, he discovered that very tiny behind my right eye was a tiny benign brain tumor, which was very naked to the naked eye. It was about 1 millimeter in size, so it was very hard to find. And of course, I've been misdiagnosed many times trying to discover what I've had, but this problem, I'm not alone in this problem. According to a study by the Johns Hopkins School of Medicine, about 12,000 Americans suffer from, 12 million Americans suffer from misdiagnosis from doctors, and from 30% of those can result in death. Now, of course, misdiagnosing with doctors is, we're humans, we can't really help that. But what if we can mitigate this problem by having artificial intelligence make the medical diagnosis, and maybe my brain tumor would have been more prolific to a AI versus a human doctor, which might not be able to see that well. So my research, I plan to have explaining an AI's generative, I'm so sorry. I got really nervous. Okay.
Take your
So for my
time.
research, I'm so sorry about that. So with my research, my goal is to have human understandable explanations to AI so that humans can trust and verify that the AI is diagnosing or giving them the correct medical diagnosis. So my plan is to have a real example of a chest x-ray and a example that is contrastive. It's very similar to the original input, but it's slightly different because you can see from here, some of the sizing are different, but I want to be able to have it to where, given that they're put into a model that's already trained to diagnose chest x-rays, I want to have kind of compare what their medical diagnoses are given from that x-ray and kind of explain what area of the image is it focusing on so that doctors can examine this and see, oh, it is looking at maybe the shoulder blade. That's not the correct area to give a medical diagnosis. So this model is not performing correctly. But for my research, I am mainly going to be focusing on, or what I have for you today, I'll be focusing on building the contrastive example, which will be this part of the research. And for this, my main goal is to build a generative model to be able to compute this counterexample. So before I begin, let me talk about, or where I begin to talk about my generative model, let me explain what my data set is. So for my data set, I want to make sure to have actual existing x-rays so that our generative model is actually accurate in generating a counterexample. So for my data set, I decided to use the Checksford x-ray data set, and it's available from the Stanford group. And basically in this study, they took a whole bunch of patients, multiple patients and multiple studies, and they took these x-rays, and it's about 224,000 x-rays. And they had 4 radiologists who are professionally trained give medical diagnosis to each of these x-rays, and so that they and they're also cross-verified to make sure that all these diagnoses are correct. But basically for this part of the generative model, we want to focus on only the images of the x-ray. The classifications or the diagnoses are not important to us, but I just want to give you a little overview about what exactly our generative model will be looking at. So for building our generative model, basically a generative model is a type of machine learning trained model or artificial intelligence that can take a basic input and generate what it should be. An example of this, what you may have seen, is prior text prediction. So sometimes you get crazy ones where it's like, I did not mean to say that, but he also meant this. But basically a generative model generates what the next thing, or it guesses what it should be next. For our generative model, I decided to use a variational autoencoder, which I will explain later, but before I explain that, let me explain what machine learning is. So to explain it, I'll be showing a neural network. It's basically one of the frameworks that are used for machine learning. It's a type of way to kind of help a computer learn. So basically, it consists of 3 layers: an input layer, a hidden layer, and an output layer. The input layer is basically what our image would be. It represents each of the features of the input data. And each of the features are represented by neurons, which are these little circles here. And each of these layers are connected via weights. So if I isolate this, you can kind of see how this neuron is connected to everything in the hidden layer. So basically what happens is these weights signify how activated a neuron is, or how much this neuron impacts this neuron. So you can have a 0 weight here, and that means that this feature of the input data is not important to this part. And then in this hidden layer is basically an extra room to do computations. And then based on which of these neurons are important towards giving a diagnosis, then it will show like what weights are here. And basically, when calculating these weights, this is done during simple calculations, and we do a forward pass going first, and then we calculate the weights, and then we do back propagation, or we do a back pass starting from here, and we calculate the weights again. So that's how we can verify that the weights are actually correct. Basically, we want to have our weights be able to where if you put in any new input, then these weights are already pre-calculated, and it should generate a correct diagnosis or classification, as called in, or as we call it in the machine learning world. But with deep neural networks, hence the title Dr. DNN, it stands for a deep neural network, it just has more hidden representations or more hidden layers here. And that basically kind of fine tunes what the weight should be. So you get like more accurate classifications or diagnosis from these. So now back to our variational autoencoder, we basically take an input and it goes through an encoder. Basically what an encoder does is that it takes a large input and it compresses it down really small. And then from there, it takes 2 separate layers, a mean and a log variance, to develop a latent space, which is our sample space from our encoder. And then from there, it takes, gets upscaled again to a bigger size input, and that gives us our reconstruction image. Now, what a reconstruction image is during training, our variational autoencoder will be trying to mimic what or trying to guess, or I refer to it as mimicking. It's basically, it's learning how to generate this X-ray. And this is the reconstruction image. It's basically what's outputted during training of the VAE. So you can see right here, it kind of guesses what it should be. It has the general shape of it. And then at the end of it, we should be able to generate an example. Our goal of our VAE is to have a perfectly mimicking training or reconstruction right here. And then for our generating example, we want it to look like it could exist in the original data set, and it could actually be a real chest X-ray. So for the first part of variational autoencoder, we need an encoder. Basically, it takes in the input. Our original image size is 320 by 320, and then it condenses it down to a 1-layer 512 representation of the data set. And basically for the each of these layers are made up of convolutional 2D layers, and basically it just takes a big image and it compresses it down to like a little bit size. I'll explain the math to you, but I don't want to overcomplicate things. And then for our latent space, basically what it is the hidden representation of our input. We want it to be able to generate, or we want our compression, or the main goal of our encoder is to have the compression down so well to where the latent space is able to sample from it, and it can actually, in a small sample space, it can actually represent what the original giant chest X-ray could have been, or what it does look like. And then for the decoder, it's exactly the same as the encoder, except in reverse. It takes in that small latent space representation, and then it increases the size to where it is the original size of the chest X-ray. And then to make sure that our reconstructions are actually correct, we have a loss here. And for this, we're using the evidence lower bound, and it's basically the mean squared error loss, which is testing to see if the what the output should be matches what the output the variational autoencoder is giving. And then and then it adds on a KL divergence. The KL divergence basically makes sure that the latent space representation keeps all of the classifications that it could be separate from one another, but then it also makes sure that ones that are similar together are put together. So like say if we were training a data set of numbers or trying to get a VAE that's able to generate new numbers, we would want all the ones to be grouped together and not have like ones be separate representations, and it will mess up what you're trying to generate. And so part of our testing to make sure that our variational autoencoder was correct, we did several optimizations and variants of the versions of it. And for one of the versions, we implemented one where we added gamma. It was part of another research paper. And basically it just adds a 1/2 term to the MSE loss. But sadly, after training, it did not have any mimicking during reconstruction, and then also generated a generic like chest x-ray. And then another test, because interestingly enough, after testing gamma, I decided to test one where no KL divergence, but obviously KL divergence is very necessary to variational autoencoders. The equation that I showed previously with the MSE loss and plus the KL divergence for the elbow or the Evans lower bound, it's a required term for variational autoencoders, but it was giving perfect mimicking for reconstructions. However, we got a very sad generated example, and the generated example is the important part of the research, because this is going to enable us to be able to produce that counterfactual example that we need to give the human understandable representation. And then so we decided to introduce KL divergence within the after epoch 25. Epoch is basically how many forward and back passes you do. So right here, it is perfectly, it's sort of mimicking, which is what we want. Then right afterwards, it stopped mimicking, which, and then the generated example is the same one that you saw with the gamma. So in the end, we decided to go with a variational autoencoder model that was pre-trained, or one that we trained. We decided to go with the version that had KL divergence, the MSE loss. It was the original formula that was shown on the previous slide, and no extra gamma terms. So what we did was we took a partition of the data set. We took 50,000 examples and we trained with that for 1,000 epochs. And we were able to produce a model that does mimic the input during training, but also generates an example that shows a chest x-ray that does look of human origin. You can kind of see the shoulder blades here and then the lower part in the sternum. You can tell I'm not an anatomy major. But sadly, this cannot be used as our counterexample because it's missing some crucial details such as the rib cages, and it's sort of blurry, which is kind of common for variational autoencoders. So once we have a variational autoencoder that has a good generated example, what's ahead for this research is actually generating the human understandable explanations. So part of what my mentor, Dr. Christian Shelton's, his previous PhD student, they had a research called Contrastive Deep Explanations. Basically, what it does is it takes in the counterfactual example that's generated from a GAN, which is another type of generative model, and it produces an output that shows which part of the image is the trained model supposed to give out the correct guesses. So basically what this data set is a celebrity data set, and they trained a model to be able to kind of guess the hair color of a celebrity. But when they put this through their contrastive deep explanation, it found that in order to give like what the hair color of the celebrity is, it was actually focusing on the color of the eyes, which is obviously incorrect because you don't look at the eyes to determine the color of the hair. So they were determining that the model was actually focusing at the wrong areas. And this can actually be crucial for when we use this in the medical field, because if, let's say, if it, as I showed earlier, if it's looking at the shoulder blades instead of the actual area of like the chest in order to give a diagnosis, so it might say like you have pneumonia, but it's like based right here, then obviously your model or your AI that's giving you a medical diagnosis is misbehaving, and it could ultimately lead to death for the patient if it is giving these diagnosis, because it could be telling you the right diagnosis, but you want it to be able to verify that it actually is giving you the correct diagnosis for the correct reasons. Oops. So in the end, it is important for our model. Hopefully for the next steps, we're able to get the contrastive deep explanations for this and give a example of showing that the a model that's given to give diagnosis is actually used for this. For the next steps, there is actually, because for the data set, the reason why Stanford Group actually released that data set was to have machine to have basically it was a competition for professionals to kind of train their own models to actually give the diagnosis for the chest x-rays, which is not something that we focused on for our research. And there was a model that was pre-trained and it had a 91% accuracy rate. So we were going to use one of those pre-trained models and use our counterexample produced from the variational autoencoder and the original input to generate which part of the images that it's actually focusing on for the diagnosis using the contrastive deep explanations from previous students' research. I would like to thank my mentor, Dr. Christian Shelton, for his patience for getting through with me. And thank you guys. Are there any questions?
Heidi, I think you can stop recording now.
Oh, thank you.